In this lecture, we will discuss about pumping lemma. Pumping lemma is used to prove that a language is not regular, and pumping lemma is based on the pigeonhole principle. Now, what is pigeonhole principle? Pigeonhole principle is that if I allocate n number of pigeons in m number of holes where the number n is greater than m, then there must be at least one hole where I have to accommodate more than one pigeon. So, I am writing it down. Greater than n, then there must be at least one hole where I have to accommodate more than one pigeon. It is basically a simple concept. If I have n number of holes are there, n number of holes and m number of pigeons, and m greater than n. So, there must be at least one hole which consists of more than one pigeon. So, this is the basic principle of pigeonhole principle. Now, based on this, the pumping lemma is based. Suppose if I consider a language LG equal to, suppose, a b square c, where sigma belongs to a b. Now, if I construct the finite automata of this language, then it would be finite automata means it may be NFA or it may be DFA. Now, for the time being I am drawing the NFA. Now, how many states are being required to construct this NFA? That means 5 states are required, and how many alphabets are there? 4 alphabets. Now, again if I consider another language LG equal to A, B and C, where n greater than equal to 0. Right. Now, if I construct the NFA in this case also, what I will get? So, now see that in this case, in the first case, if we consider the first case, in this case what happens that for the 4 alphabets I require 5 states. Now, if I consider the alphabets as the pigeons and the states as the whole, then the number of holes are greater than the number of pigeons. That case there is no issue. That means each hole can accommodate one pigeons, and that means each state that are consuming one alphabets. But in this case, if the number of states are 3 and number of elements are n plus 1, sorry, not n plus 1, it should be n plus 2, because n number of b is there and one a and one c is there. So, the total number of alphabets are n plus 2, and whereas the number of element states are only 3. So, if I consider this number of alphabets as the pigeons and the states are as wholes, then what will happen, that obviously the number of pigeons is much more than the number of holes. So, in pigeonhole principle we told that there must be at least one hole where I can accommodate more than one pigeons. Here also there must be at least one state where I have to consume more than one alphabet, and this one is this Q1, which is consuming more than one alphabet. Means that if there are more alphabets than the number of states required, then there must be at least one state where I have to pump multiple numbers of alphabet inside it, and that is the basic principle of pumping lemma. And based on this pumping lemma, we have to prove that a language is not regular. Now, let us write down the pumping lemma. Let L be a infinite regular language. What is infinite? A language whose length cannot be determined in runtime. Then there exists some positive integer m such that can be decomposed as omega equal to x y to the power I z, where mod of x y less than equal to m and mod y greater than equal to 1. What is m? M equal to the number of states required to construct the DFA. So, again I am telling that if L is a infinite regular language, then L can be represented with the form x y to the power I z, where mod of x y less than equal to m, where m is the number of states required to construct the DFA, and mod of y greater than equal to 1. So, if I can form a language in accommodate, or if I can represent a language in the form of x y to the power I z, then I can say that language is regular, otherwise not. Now, let us see some example. n bn n greater than equal to 0. Already you have seen that this language is not a regular language, because we cannot form the regular expression. The a star b star cannot be a regular expression for a and b n. Why? Because a star does not guarantees that the same number of a will appear in b star also. So, a can increase in its own term and b can increase in its own term. So, a and b n is not a regular expression for a star b star. Now, how to prove it? As we cannot construct a regular expression out of this, so it is not a, regular. Now, you have to prove it using pumping lemma. pumping lemma tells us that I have to represent the language in the form of x y to the power I z, where x y z is constant, but I can vary from 0, 1 to up to dot dot infinity. Now, let us use the method of contradiction. That means, first initially consider that a and bn is a regular language. If a and bn is a regular language, then a and bn must be represented in the form of x y to the power I z. Now, if it can be represented, now let us try to accommodate all the elements, that means n number of a and n number of b in x y to the power I z. Now, out of this n number of a, let us put p number of a to x, then n minus p number of a to y, and the rest of the n number of b to z. Means I have total n number of a is there, n number of a is there, and n number of b is there, right. So, I have to accommodate these elements to x y to the power I z. Now, what I am doing, that p number of a I am accommodating at x, n minus p number of a, rest of the a I am accommodating in y, and n number of b I am accommodating in z. Or on the contrary, I can consider three fixed containers x, y and z, right. Now, in x I am accommodating a p, in y I am accommodating n minus p, and in z I am accommodating n number of b. In such a manner, there should not be any underflow or overflow. Now, x, y and z is fixed, but I is not fixed. I can vary from 0 to n, right. I can vary from 0 to n. Now, if the value of I increases or if the value of I decreases, that case, to make it perfect filling, what I have to do? I have to either increase n minus p or I have to decrease n minus p. So, if I have to increase n minus p, either I have to increase the value of n or I have to decrease the value of p. Now, as n and p is associated with x and z, so neither I can increase the value of x or the value of p, or nor I can increase the value of n, that is z, because both are constant. So, whatever we have assumed that we can increase the value of we can increase or decrease the value of n and p respectively with respect to the increase of I, that is not possible. Means that our initial assumptions to accommodate n number of a and n number of b at x y to the power z is totally wrong. So, we cannot accommodate n number of a and n number of b to x y to the power z. So, the language is not regular. Now, let us see that the other languages, that means for which we can construct a star b star, that is a and bn, where n greater than equal to 0 and m greater than equal to 0 for this language. That means the regular expression is a star b star, as we can construct the regular expression for a and bm. So, it is a regular language, right. Now, we should accommodate n number of a and m number of b to x y to the power z. Now, let us see that how we can do this one. Now, in this case, if I consider x y to the power I z, now consider the same case. I am accommodating p number of a to x, n minus p number of a to y, and n number of b to z. Now, similar case, x and z is fixed. I cannot change x and z, but as I can be increased, the value of n minus p may increase or value of n minus p may decrease. Now, if I consider the n minus p, to increase it, either I have to increase this value of n, or I have to decrease the value of p. Now, in this case, I can easily the p cannot be decreased, because p is associated with x and x is fixed. So, as I cannot reduce the value of x, x is fixed, this one should be m. because it is m number of b, but easily I can increase the value of n over here because n is not associated with either x or z. So, I can increase n easily. So, why it is possible? Because in this case n number of a and m number of b, in this case I can easily increase the value of n and with the value of m, value of a and value of b also. Any number of a I can consider or any number of b I can consider, but they are not related to each other. They can increase on their own term, which is not possible in the previous case. Whatever be the increment we are doing in case of a, the same number of increment we have to do in case of b also. So, the earlier case it is not possible to construct finite automata, because the one of the limitation of finite automata is that it is memoryless. So, if I have to keep track of how many number of a is increased and I have to keep the same number of b to be increased, I have to keep one memory, which is not possible in case of finite automata. That is why a n b n is not regular. On the contrary, a n b m is regular, because a can increase on its own term and b can increase on its own term. They are not related to each other, and that is the same case for which I can accommodate a n number of a and m number of b to x y to the power I z, and that is why it is regular. Hope through pumping lemma how we have proved it, it is clear. Now, let us consider another problem, that is Lg equal to omega omega r, where omega r is the reverse of omega. Now, if I consider omega equal to AB, then omega r will be BA, means omega r is the mirror symmetry of omega, that means it is AB BA. Just simply it is a palindrome. Now, if it is a palindrome, then it should not be a regular language. So, how to prove it? Obviously, because how many number of the alphabets that are coming in case of omega, the same number of alphabets that should come in opposite order in case of omega r. So, we need to keep one memory, which is not possible in case of a finite automata. So, it is not a regular. Now, how to prove it using the pumping lemma? The same way that we have used in the earlier problem, we will use the same technique to accommodate this language to x y to the power I z. If it is possible, then I will say that it is regular, otherwise it is not regular. Okay. Now, in this case we will not bother about that in omega what are the alphabets are there, we will bother about only the what is the length of omega. So, if the length of omega is n, then length of omega r will obviously be n. So, my total number of elements will be n plus n, that is 2n. So, we have to check that whether twice n number of elements can be accommodated in x y to the power I z. Now, we will use the same technique, put p number of alphabets to x, n minus p number of alphabet to y, and n number of alphabets to z, so that the total element twice n number of elements can be accommodated to x y to the power I z easily. Now, the value of x, y and z all are constant, but the value of I is increasing. So, the y to the power I will get increased. Now, to increase y to the power I, either I have to increase n or I have to decrease p. So, none of this is can be possible, because it is associated with x and z. So, this is not regular. Similar manner, I can prove that Lg equal to omega omega, where omega belongs to AB. So, this language is also not regular. So, the same manner we have to prove it, that mod of omega is n, then the total length of the language is twice n. So, we have to check that how to accommodate twice n number of elements to in x y to the power I z. If I can accommodate it, then it will be regular, otherwise it is not a regular language. Now, let us see that Lg equal to a to the power I square, where I greater than equal to 1. That means a perfect square value, that is not a regular, using pumping lemma, not a regular. Now consider it is true for any value of I, so it should be true for I equal to m also. Let us consider I equal to m. Let us consider I equal to m. What is m? M is the number of states to construct the finite state machine. So if the machine the length is a to the power of m square, and that is equal to Lg, or that is equal to omega equal to a to the power of m square, then what is mod of omega? Mod of omega equal to m square. Okay. Now, and another thing that we know, that mod of xy, that is less than equal to omega, and mod of y is greater than equal to 1. Now, as we have earlier told that if I can represent a language in the form of omega equal to x y to the power I z, then I can say that language is a regular language, and that is true for any value of I. That is true for I equal to 0, I equal to 1, I equal to 2, I equal to 3. Now let us consider if I equal to 1, if I equal to 1, that value will be x y z, and if I equal to 2, the value will be x y square z. So if I can represent the language in the form of x y z or x y square z, that case also I can say that the language is a regular language. Now let us consider for I equal to 2, that is x y square z, omega equal to mod omega equal to mod of x y square z, and so this should be mod of x plus 2 mod y plus mod z, and we have seen that mod x plus mod y plus mod z, that is also equal to omega, right? Now this should be equal to m square. This must be greater than m square. Why? Because my language is m square, so this should be equal to m square, and this one is greater than m square. Why? Because we know that x y z is omega, and that is equal to m square, that we got it from here itself. So if I consider that omega equal to x y z, that is equal to m square, and with that we have mod of y also. So we can easily say that this one mod of x plus mod of y plus mod z plus mod of y is greater than m square, because mod of y again is greater than equal to 1. So that is one thing, that mod of x y square z is greater than m square. Now let us consider another thing, that omega equal to that is omega equal to x y square z, right? Now as mod of x y less than equal to m, then mod of y must be less than m. Now here I have mod of omega equal to mod of x y square z, that is mod 2 mod y plus mod z, that means mod x plus mod y plus mod z plus mod y. If I write it down, then that mod of x y z is equal to m square, right? And mod of y, I am writing it, in this case mod of y is less than m. Now can I write mod of x y z plus mod of y is less than equal to m square plus m, because this y is less than m and this x y z is equal to m square. Now with that, if I add mod of x y z plus mod of y, less than equal to m square plus m plus another m plus 1, means we are adding m plus 1, we are adding m plus 1. So if I add m plus 1, then it must be less than equal to less than m plus 1 whole square. Now in earlier case, if you look at the earlier case where we have seen that x y square z is greater than m square, and in this case we find out that x y square z is less than m plus 1 whole square. Now can I write that x y square z is less than m plus 1 whole square and it is greater than m square? So x y square z, which is equal to omega, is not a perfect square value, it is in between two consecutive perfect square value. So if this value is not a perfect square value, then what is our initial assumption? That this perfect square value a to the power of I square is a regular language. That is totally wrong. So hence it is proved that LG equal to AI square, where I greater than equal to 1 is not a regular language, is not a regular. Now let us consider another problem. Where p is a prime number then omega equal to a to the power k. Now consider that k is a prime number. In this case, instead of a to the power p, I am considering it is at a to the power k. Then mod of omega equal to mod of a to the power k, that is equal to k. So that means omega equal to k, right? And it must be greater than m. What is m? M is the number of states. Now as well as we know that mod of x y less than equal to m and mod of y greater than equal to 1. Now consider x y to the power I z, that is equal to mod of x plus I mod of y plus mod of z, that is mod of x plus y plus mod of z plus I minus 1 mod of y. Now this one is basically k, right? Already we have seen that this one is basically k plus I minus 1 mod of y. Now this one is k and this one is I minus 1 mod of y. Now let us consider the length of y is t. Let us consider mod of y equal to t, right? Now if mod of y equal to t, then it will become k equal to I minus 1 into t. Now this must be true for any value of I from 0 to infinity, right? Now that means it must be true for I equal to k plus 1, I equal to k plus 1, one arbitrary value we have taken. Now I equal to k plus 1, it must be true. That case it should be k equal to k plus 1, k equal to k plus 1 minus 1 into t, means should be k into kt. If I take common, then it is k into 1 plus t. Now this value can never be a prime. This value can never be a prime number for any value of k. So this number can never be a prime number for any value of k. So whatever be our assumption that x y to the power I z is a prime number, that is totally wrong. So if x y to the power z is not a prime number, so we can never represent a to the power p in the form of x y to the power I z. So it is not a regular language. So in this way, there are several problems that we can use pumping lemma through the method of contradiction to prove that the language is not a regular language.